Hey guys, so this is just the continuation of 10.3. I'll try and be as brief as possible as I can. We talked about the alternating series error bound, which essentially just says that the error, the error, whenever I take the sum of the function and subtract my partial sum, that's how much difference there is, that's how much error there is in my approximation. Well, if it's an alternating series with this criteria, then the error, whatever it has to be less than or equal to the nth plus 1 term, the absolute value of the nth plus 1 term. So, with that being said, we are going to focus a little bit more on the Taylor polynomials now, on the power series and what those mean. Okay, so here's a geometric series right here, and it is a power series. So find a formula for the truncation error if we use 1 plus x squared plus x to the fourth plus x to the sixth to approximate this function right here. So we say f of x is equal to 1 over 1 minus x squared. Definitely looks geometric, and it's over the interval from -1 to 1, and we're saying that this polynomial is represented by, or this function has the polynomial representation of 1 plus x squared plus x to the fourth plus x to the sixth. Now, say I continue this, it looks like the pattern is x to the eighth plus x to the 10th plus x to the 12th, and so on. So you can see that we're truncating this polynomial right here. Now, the idea of the alternating series still stands. This right here is my error. Again, if I were to use the notation as before, but using more function notation, so f of x is the actual sum of this polynomial, and what we're saying is that it's equal to, well, we're using the, excuse me, excuse me, we're using the, looks like to be the third derivative. I say third derivative because this follows very closely to 1 over 1 minus x, which is equal to 1 plus x squared plus x to the third. So it is a third order Taylor polynomial. It's just that we're substituting x squared into all of these right here. So this is a third order Taylor polynomial. Okay. But it's not quite equal to unless I include my remainder or my error. I'm going to call this R3 of x. So R3 of x represents the entirety of my polynomial that I am truncating. Okay. Now, good thing is that this, in this case, it's a geometric series, unlike the series that we used before, which were basically just alternating. So with alternating, I was able to find a bound of the error. Now for geometric series, I can actually find either if it's a power series or if it's just a regular geometric series, I can find an exact equation for this right here, because this is a series in and of itself. It's a geometric series right there. And remember that a geometric series converges to 1 over 1, excuse me, converges to a sub 1 over 1 minus r. Well, since this right here is a geometric series, excuse me, a sub 1 is equal to x to the 8th, and my common ratio is equal to x squared. So, r sub 3, which is my truncation error, I can actually find an exact equation that can sum up the error. And that's going to be equal to x to the 8th divided by 1 minus x squared. So, and there you go. So now if I were to use this to approximate a value between 0 and 1, so say I wanted to find f of 1/2, well, I could find the exact difference or the exact error by plugging in 1/2 into this function right here. That will tell me, so if I plug 1/2 into p of x, that tells me the approximation. If I plug 1/2 into r of x, that will tell me my error, how much of a difference there is. Okay, so this is the case for geometric series, and that includes power series that are geometric. Okay, So there's another type of an error. Now the last one that we're going to talk about is for Taylor series, and it's called the Lagrange error bound. This is the bound, but it kind of it extends from this idea, and it also extends very closely from the alternating series error bound. Now, the thing that's different is that in Taylor series, um, it might not be alternating. It might be alternating, but we can still apply the same idea as the alternating series error bound, which is the nth plus one term is the highest that it can be. So let me talk about the definition of the Taylor series. So we know that in a Taylor series, that the first term a sub 0 is essentially just f of c. So c is the center of where you're approximating your function, your polynomial. So a sub 0 is f of c. Then the next term, we would take the first derivative, right? We would take the first derivative and we would divide it by c, or we would divide it by 1 factorial. That's just going to be 1. And then multiplied by x minus c, so wherever it's centered at. And then the next term, well, to find the coefficient, it would be the second derivative at c divided by 2 factorial, and then x minus c squared. And then we would keep going on and on and on. So if I wanted to talk about whatever the nth term is, this would be the nth derivative at c divided by n factorial times by x minus c to the nth power. And of course it keeps going. And again, if we choose to truncate this, let's say we truncate this polynomial at the nth term, well, there's going to be a remainder. So we're just going to call it plus Rn of x. Okay. Now Taylor, the guy who came up or who studied these series right here, well, he theorized, or I think he actually came up with a proof where he could find the exact value of R sub n in a Taylor series, which is pretty cool considering that it goes on forever. But you can find it because it can't the sum can't go on forever. So for example, we talked about it here. So here is a Taylor series with the sine of x. Well, and again, if we talk about what's happening at 1, the error is not infinite. The error is very small, actually. But Taylor was able to find a formula that where you could actually find what R sub n is. And this is it right here. So R sub n, which is the error, he found that it was equal to it had to deal with the next term that came after of this term right here. So the term that comes after this, let's call the term after this f of n plus 1. So you'd have to take the next derivative after n. You'd have to do n plus 1 factorial, and then it would be x minus c to the n plus 1. So this is the term that comes right after this right here, after our truncation. So the error would be equal to, he said that he could find the error, and he said it was equal to the nth plus 1 derivative at z. So I'm going to talk about what that z is. Divided by n plus 1 factorial times by x minus c to the n plus 1. Now, this z is really, really weird and hard to describe, but it is a value, z is a value that is between x and c, where c is the center of the polynomial approximation, and x is the value we're approximating, is the value of approximation. So if you need to pause it to finish writing, I'm going to jump to another screen. So here's what he's basically saying. He says that this distance that's between, so you can see where x is equal to 1 at the bottom of the screen, that difference between the function, you can actually find that exact difference by using that formula. So he's saying that there is a value between 0, in this case 0 is where we're centered at, and 1 is the value of approximation, but there is a value in between there where if I take the nth plus 1 derivative at that value that's between 0 and 1, that it will actually give me the exact value. Now, the thing is, we do not know how to find that value. This right here is really not, we can't find it. He might have a way of finding it, but for our purposes, we cannot find it, and we don't need to find the value of z. So that's what Taylor theorized, and then Lagrange kind of expounded off of this. Well, and that's what we're going to use. So this is the Taylor remainder, but we're going to be using the Lagrange error bound, which builds off of this right here, and the fact that we cannot know what z is, but that it's between these two values. So the Lagrange error bound says this right here. Very similar to the alternating series, but he says that the absolute value of our approximation is equal to, so I'm going to switch these spots right here, doesn't really matter because they're both on the numerator, is equal to the absolute value of x minus c raised to the n plus 1 divided by n plus 1 factorial. So basically this right here is it's the nth plus 1 term. Now the coefficient of that right there, or part of the coefficient, this is what's different. You multiply it by the max value of n plus 1, the nth plus 1 derivative at z. Okay, so this right here is the Lagrange error bound. This is what we're going to use. And so instead of actually finding the exact value of z, which we won't be able to find, what we're going to do is choose c or x. One of these values right here will give us a maximum value of this approximation. So we're going to approximate this value right here by using c or x. Whichever one will make this entire error greater than, will make it the largest it can be. That right there will be the bound. So it's kind of like the alternating series where instead of finding the exact value of the error, we're just going to create an upper bound of what the error can be. So it's a very, very abstract idea. Probably one of the most abstract ideas that we've covered, mainly because of this z. It gives us such a hard time because we want to know what it is, but we just don't have a means of finding it. Okay? So it's hard to just keep talking about it. It's better if we just go over some questions. And again, the book does a pretty awful job of practicing, of giving you good questions that are like the what you see on the AP exam. So I went ahead and in the AP classroom, if you go there, there is a Lagrange error bound quiz. It's multiple choice. I recommend that you go through it if you want to try it on your own, but I'm going to go through the same problems right here. Okay, so the Taylor series of the function f about x equals 2 is given by this function right here. So it's centered at 2 right here. You can see it's alternating, okay, and here's a coefficient. So here's the Taylor series, and it converges over the interval from 0 to 4. So again, it's pretty obvious to see that 2 is the center. Okay, if the third degree Taylor polynomial for f about x equals 2 is used to approximate f of 9 over 4, what is the alternating series error bound? So this is kind of going to highlight that the alternating series error bound and the Lagrange error bound are very similar. Okay, so this is alternating, so we can use the alternating series error bound. Now, remember what the alternating series error bound said. So in this case, we're using p sub 3 of x to approximate f of x. The alternating series error bound said that that this r sub n of x, that the first term of this has to be the max error. So my error, so the absolute value of r sub n of x has to be less than or equal to the fourth term of the polynomial. So this right here has to be equal to has to be less than or equal to p sub 4 of x. And that's really all you need to do. So that's what the alternating series error bound says, is that the remainder has to be at least the next term, cannot be greater than. So what is p sub 4 of x? First of all, let's find p sub 4 of x. So let's go ahead and plug 4. So 0, 1, 2, 3, or maybe we want to plug in 3 into that. Yeah. No, I think we want to plug in 4 because we want it to be to the fourth. So third, yeah, we want to plug in 4. So if I plug in 4 into that, I get negative 1 to the fourth, which is going to be positive. Okay, and then I'm going to have 3 times by 4 plus 1 over 2 to the fourth, and then x minus 2 to the fourth. So this is going to be equal to 13 over 16 times by x minus 2 to the fourth. And we are approximating at x equals 9/4, so let's just plug 9/4 right here. So this is going to be equal to, you might actually already be able to see, it looks like it's going to be one of these two. It looks like that's what our answer is shaping up to be. So 13 over 16, and then we have 9 over 4 minus 2. Now 2 is 8 over 4. So we get 13 over 16, and then that's going to be 1 over 4 to the fourth, which is going to be equal to 13 over 16 times 4 to the fourth. So that's the maximum my error can be, and there we go, that's C. So again, kind of just to sum up what we did, so we're using p sub 3. The third degree polynomial, Taylor polynomial, is used to approximate our function at this value right here. The alternating series error bound, which this is alternating series, says that the remainder has to be less than the term that precedes the term after the truncation, where the truncation occurs. That's p sub 4. So just plug in where you're approximating at, and then this right here will be the maximum that our error can be. Okay. Let's try this one right here. So let f be a polynomial function with non-zero coefficients. Okay, so here we have our function right here. Looks like this is a fourth degree. T sub 3 is the third degree Taylor polynomial for f centered at C, such that, so this is what it would look like if it was centered at C. So based on the Lagrange error bound, f of x minus t sub 3 of x must be equivalent to which of the following? So the Lagrange error bound. Just let's default to our definition. That's what I like to use. Just default to the definition, and I think it makes a lot more sense. So based on the Lagrange error bound definition, so if you need to go back and look at it, go for it. It just says that the remainder is equal to the nth plus 1 derivative at z all over n plus 1 factorial times by x minus c to the n plus 1. So that right there is what our remainder is. Okay, so we're saying that it has to be equal to, that's what we're trying to find out. Okay, so let's think about what this part, so if we're using, one second, so we're using a third right here, so that means we're trying to find r sub 3. So r sub 3 of x, so we're using 3 for n, which means we're going to take the fourth derivative, which makes sense, and the fourth power, because we're only going to the third. So after we truncated this polynomial, this is going to be the next term that comes after it. So then this is going to be the fourth derivative at z divided by 4 factorial times by x minus c to the fourth power. So just to kind of explain my thinking is that, because this is so very general and basic, it's hard to use examples, but I see this Lagrange error bound. I think about the definition, and now I'm trying to apply the idea of the third and then to the fourth. So I'm trying to apply any specifics that I can, even though it's kind of hard. So I use the definition. Well, the Lagrange error bound, I'm using the third term, or the third degree, which means my remainder has to be based off of the fourth term. That's the fourth derivative, the fourth factorial, and the fourth degree. Okay, so what is this so the Lagrange error bound, what is this going to be equal to? So let's think about what the fourth derivative is right here. So that's what I want to think. So what is the fourth derivative of the function right here? So if you think about the fourth derivative of the function right here, well, the fourth derivative, that's going to be 0, that's going to be 0, that's going to be 0, this is going to be 0. Now this right here, if I take the derivative of this 4 times, I'm going to drop the 4, I'm going to drop the 3, I'm going to drop the 2, I'm going to drop the 1, and that's going to be just going to be x to the 0, which is going to be 1. So this derivative at z is actually going to be equal to 4 factorial, okay? And then because this is going to be to the 0 power, I don't have to plug in z. So it's going to be 4 factorial times by a sub 4. This right here is going to be equal to the fourth derivative of the function. But there's no need to plug in z. So with that being said, let's use that right there. So r sub 3 of x is equal to 4 factorial times by a sub 4 times by x minus c to the fourth divided by the 4 factorial that we had over here. So those are going to go. So my r sub 3 of x, my error, is going to be equal to a sub 4 times by x minus c to the fourth. And that looks like it's going to be c right there. So this one is probably a very difficult one because it's hard to really understand what's going on, and especially since you're so new to experience the Lagrange error bound. This is so new to you. But again, start with the definition. It's asking you to use the Lagrange error bound. Here's the Lagrange error bound. Okay? And then it's asking us to, what is the Lagrange error bound going to be for third terms? Well, use the fourth term after that. And then we use the function right here, and we use the fourth derivative to evaluate this portion right here, and that eventually led to this answer right there. Okay, one more problem right here. So let p of x be the fifth degree Taylor polynomial centered at 0. Information about the maximum of the information about the maximum of the absolute value of selected derivatives of f over the interval from 0 to 1.2 is given in the table above. Of the following, which is the smallest value of k for which the Lagrange error bound guarantees that f of 1.2 minus the polynomial approximation is less than or equal to k? So confusing, not gonna lie, so very confusing. But I know that it's asking me to use the Lagrange error bound, so I'm going to use the Lagrange error bound. So r sub, in this case, I think we want to use r sub 5. So I say r sub 5 is because we're using the fifth degree polynomial. R sub 5, though, is equal to the f of 6, so the sixth degree. Okay, so this is going to be equal to the sixth derivative at z divided by 6 factorial times by x minus c. In this case, it's just going to be x because it's centered at 0. So x raised to the 6th power. Okay, so which of the following k values guarantees that f of 1.2 minus p of 1.2 is less than this value right here. Okay, so this is the value we're looking for. So k has to be equal to this right here. K has to be equal to this value, because this right here is this right here. That's what this is supposed to be equal to. So the difference, this means error. So the actual value of the function minus the approximate value of the function, that is this right here. So r sub 5 of 1.2 is equal to the sixth derivative at z over 6 factorial times by 1.2 to the 6th. And we're saying that this has to be equal to k. Alright, so now we can just solve for k, but note that we're going to have to replace the maximum value. So since we don't know what z is, we're going to maximize this value right here. So you can see that we're given f of 6, f the sixth derivative at x here, so that's what this table was for. It was to provide it. So note that since we can never really find this value, hopefully it brings some comfort to you guys that it has to be given, a maximum value has to be given to you. So again, what we said was that we can't find z, so we want to maximize this value. Well, here's the maximum value between 0 and 1.2 that will give us an error bound. Since we can't find the actual value, we're going to maximize it and create a bound. So the maximum value is given to us, so k is equal to 58.8 divided by 6 factorial times by 1.2 to the 6th. And if you punch that into a calculator, I think it comes out to be about 0.244. So that would be C. Okay, so that's all the AP practice problems. If you need to go through and study them more, please do so on the AP website and refer back to this video. Okay, now only last thing I want to talk about is what you'll more than likely see, or what you are going to see on your homework. Okay, so just briefly I'll talk about your homework. I believe I assigned the problems. Let me check really quickly. So for 10.3 it's 1 through 9 odd. So in 10.3, 1 through at least 1 through 9, you're just going to use the Maclaurin series table and build out the series. So you already did a little bit of that in 10.2, so that's nothing new. So it doesn't really have anything to do with the Lagrange error bound. So 1, 3, 5, 7, and 9, you're just going to build out these functions into polynomial series using the Maclaurin series table. Okay, I think you have, let's see, 13, 14. These are geometric series. So you're going to find the formula for the truncation error, which I gave an example of in this video, the first thing we talked about. And then 19 and 20, this is where you're going to use the Lagrange error bound and alternating series error bound. And I'll give you an example of what this might look like in this problem right here. So give a bound of the error using the Lagrange error bound for f of x is equal to e to the x when x is equal to -1. So essentially, f of -1 is equal to e to the -1. Okay, so we're going to find the maximum error of this compared to e to the x, but we're going to be using the polynomial. So that's essentially what it says here. So suppose you have a Taylor polynomial and we're approximating sine of 0.5. What's the maximum that this is going to give in relation to sine of 0.5? So what we're going to do is we first need our Taylor polynomial. So if I use the Maclaurin series table, which is what you probably want to use, you'll see that e to the x is equal to 1 plus x squared divided by 2 factorial plus x to the third divided by 3 factorial plus x to the fourth divided by 4 factorial plus x to the fifth divided by 5 factorial. And I don't know why I chose 6 terms. I probably should have done shorter. Plus x to the 6th divided by 6 factorial. Okay, so I guess we can say this is approximately. Okay, so what we want to find is the error bound. So the Lagrange error bound. So r sub 6 of x, that is going to be my error bound, which is going to be equal to, it has to be equal to the seventh term. So in this case, it's going to be the seventh derivative at z over 7 factorial. And then this is centered at, I guess I didn't specify. This should be centered at x equals 0. So we'll just say x to the 7th. Okay, so, well, let's go ahead and plug in the value that we want to find the error bound for. So in this case, we're using x is equal to -1. So r sub 6 of -1. Note that we should probably also be using absolute value signs. It's going to be equal to the absolute value of the seventh derivative at z divided by 7 factorial -1 to the 7th. Okay, now if I evaluate this, this is going to be negative, but it's under absolute value sign, so it's going to be positive. So my error, r sub 6 of -1, is equal to the seventh derivative at z divided by 7 factorial. Now this is where we're going to maximize this value. How can I maximize this value right here? Well, remember that z is between the center point and the value of approximation. So z has to be between the center, so in this case 0, and where we're approximating at -1. So z is somewhere between these. Now I'm going to just, since I don't know what z is, I'm going to use -1 or 0. Whichever one of these two values that will maximize this value right here, well, not necessarily maximize this, but maximize this entire expression right here. That's what I want to use to give my error the most it could be. So if I use z is equal to -1, well, -1 would make this negative. Okay, so I don't think we necessarily want to do that right there. Well, maybe we do. Do we want to use that? Well, okay, first of all, think about, okay, one thing, take a step back. We have to understand what the seventh derivative of the function would be. So the seventh derivative of f of x, that's what we need. Sorry, I totally forgot about that part. So the seventh derivative of e to the x is going to be equal to e to the z, because the seventh derivative of e to the x is that many times. Okay, so, yeah, sorry, I totally forgot about that. Now it makes more sense to plug in a value. So am I going to plug in -1 or 0 into this right here to maximize this value right here? If I plug in -1, I'm going to have e to the -1 over 7 factorial, which is equal to 1 over 7 factorial times by e. So it's either that, or I plug in 0, I have e to the 0 over 7 factorial, which is equal to 1 over 7 factorial. So which is larger? This would have to be larger right here, because I'm dividing by a number, I'm dividing by e, not just by 7 factorial, which would make this smaller right here. So this right here, 1 over 7 factorial, so my error has to be less than or equal to 1 over 7 factorial, which is about equal to 0.000984. Okay, so again, not super hard, just very difficult to understand. The process isn't too bad, but wrapping your mind around, especially this part right here, is very abstract. So hopefully the practices I gave you here help. If not, please reach out to me today. I can schedule, or I can set up a Zoom conference, and we can talk about it a little bit more. Or if you have questions from 10.2, we can also talk about that. So anyways, hope these videos help.